All right, so the next talk is by Sviatoslav Borisov. He's going to be talking on multi-segment and Echelle stellar spectra processing issues and how to solve them.
Hello everyone. My name is Sviatoslav Borisov, and currently I'm a PhD student at the University of Geneva, and I'm also doing some research at Moscow State University. And today I want to tell you about some issues you might have when dealing with multi-segment and Echelle stellar spectra, and the ways to solve these issues. Yeah, so the main motivation for doing this is that because we want to model stellar populations and galaxies and star clusters and etc. And especially it is very important to do this in the infrared range because the number of observations is growing in this range, and I believe that after the launch of the James Webb Space Telescope it will start growing even more rapidly. Also, we need stellar spectra for some exoplanet science and for constraining the stellar evolution models. In my talk, I will consider two different stellar spectral libraries. One of them we developed by ourselves from scratch. As for the second one, we recalibrated the existing one. So, and I will start with Las Campanas Observatory stellar library, which we developed during the last several years. And this stellar library consists of spectra of approximately 1,400 stars. And it has a very good coverage in the space of stellar atmospheric parameters because it has observations of many different stars, including some very rare types of stars. For example, so far this is the largest set of infrared spectra of AGB stars. It also contains some spectra of stars from Magellan clouds, of brown dwarfs, etc. This library was observed with fire. This is a spectrograph mounted on Magellan Baade telescope in Chile. This is an intermediate resolution Echelle spectrograph, which covers a wavelength range from approximately 0.8 to 2.5 microns. And here you can see it's on the left figure, you can see its optical layout, which is very complex, which makes data processing very difficult. And now I will tell you more about these difficulties and solutions. So first of all, you might have some problems with the point spread function because it might be non-Gaussian, and moreover, it might be cut by Sliton 1H. And there is another type of problems is that due to some flexures in the mechanisms, the flat field frame might be a bit shifted with respect to science frames, and it produces some ripples in the regions where Echelle orders overlap. So, but there is a solution to this. First of all, you have to use empirical PSF and perform optimal extraction using it. So, and as for this shifting of the flat field with respect to science frame, you need to derive the optimal value of this shift by minimizing the difference in flux in these regions where orders overlap. The second type of problems, it relates to detector and the instrument. The detector itself, it has 4 amplifiers, but they're slightly different. And it also might have some problems with pixels because they might be hot or dead, and they have different sensitivity. As for the instrument, there is one very crucial problem. Its slit position is not repeatable, which means that if you use one slit and then change it to another, and then change it back to the first one, its position is not going to be the same as the initial. So to solve this, you have not to change the slit position between calibrations and science observations. For example, we did calibrations in the daytime because we didn't need the dome open, so we could do this with the dome closed, and moreover, it saved a lot of time. As for the pixels, of course, you have to create a bad pixels list and to create super flat to correct this pixel-to-pixel sensitivity. The second problem is telluric correction. Telluric lines, they are produced by an Earth atmosphere, by oxygen and vapor, water vapor, and in the infrared range, it is also produced by methane and by carbon dioxide. And to eliminate these lines, you have to divide the observed spectra by atmospheric transmission models. But since these lines are very, very narrow, you have the wavelength solution should be just perfect. So, and if the wavelength solution is just a bit imperfect, it might lead to some very big residuals. The second type of problem with telluric correction is that the most common way to perform it is to observe spectra of so-called telluric standards. Usually they are fast rotating A-type stars. But they're not really standards. Why? Because they might have different rotational velocities, they might have emission lines in their spectra, and also some mismatch in between real atmospheric parameters and model atmospheric parameters is possible. So that is why we developed another method to perform this telluric correction without even using a telluric star. So we use a model which consists of synthetic spectrum and multiplied by atmospheric transmission and convolved with the line spread function. Also, it is possible to take wavelength shift into account in order to fix these imperfections in the wavelength solution. And then, so when we have this new adjusted wavelength solution and atmospheric transmission, we can just, as I said, divide the observed spectrum by this model. So the second stellar library is UVES-POP. Originally, it was developed by a team from ESO, and it was observed with UVES, which stands for ultraviolet and visual Echelle spectrograph. This library contains about 400 stars and with a very high resolution of about 80,000 and covers a wavelength range from 0.3 to approximately 1 micron. But unfortunately, there are some issues with it. First of all, they relate to Echelle orders merging and stitching of non-overlapping segments and some other problems. So as for Echelle orders merging, as I already said when I was talking about LCO-SL, it might be due to some shifts of the flat field with respect to the science frames. But we also, in this library, in case of this library, we also discovered a second reason, and this is over or under subtraction of scattered light in the spectrograph. So that is why you have to modify the initial algorithm a little bit and derive both the value of this shift of the flat field and the value of this over or under subtraction. And here in this figure, you can see the an example of this what we had and what we had before and what we had after this correction. Also, since the spectrograph has 3 different CCDs, there are some gaps between them. So that means that there are 2 gaps in all the spectra. But unfortunately, they were stitched not perfectly, which means that there are some jumps in the flux on the left side and on the right side of these gaps. So to solve this problem, we used synthetic spectra to adjust these segments, to adjust the flux on both sides of the gaps. And here you can see an example with original and corrected spectra. We also performed photometric correction because anyway, after all the procedures, you still might have some imperfections in terms of flux calibration. So we collected data in 33 photometric bands from these catalogs, including two space-based catalogs, Gaia and Tycho. And of course, we don't have 33 observations for all the stars, but we collected as many as possible. So here you can see an example of this correction. We just adjusted the spectra to the photometric spectral energy distribution. So in summary, I'd like to say that we have two different stellar spectral libraries with a very high quality of flux calibration, and one of them has an unprecedented coverage of the stellar atmospheric parameters in the space of stellar atmospheric parameters. And for most of the stars, we have the values of their parameters. And if you want, you can see the poster by Evgeny Rubtsov on the conference, which describes the minimization algorithm which was used for full spectrum fitting. And also visit our website of the project. Here is the link to it. And on the website, you can play with all the spectra, with fittings, with the parameters. So you will find the table with all the parameters. And this is very, very user-friendly and nice, I hope. So that's it. Thank you.
Thank you so much. Round of applause, please. Peter made a remark here on Discord that I will just read out to you. Maybe you can have a comment there. The order merging is always a bad idea and never works. To get perfectly unblazed spectra, of hot stars is impossible. Do you have any remarks on that?
Could you please repeat what is not perfect orders merging?
The order merging is always a bad idea and never works. To get perfectly unblazed spectra, sorry, now the question has moved, sorry about that, of hot stars is impossible. Do you have any remarks on that?
No, I don't agree because for example, here you can see an example where merged orders, and this is quite hot star, and as for me it looks very nice. So it is possible to merge both cool and hot star orders of both cool and hot stars without any problems.
Okay. Okay. So yeah, a follow-up remark here. How do you save Echelle spectrum to preserve all the precision? Usually people rebin the merged spectrum in one long strip, losing part. We do not have ideal format for storage of Echelle, / the VO should start to work on it.
So the question is about rebinning.
Mm-hmm.
I guess it's so I think the key point here is that you have to. I'm not sure that I'm answering this question, but first of all, you have to perform optimal extraction, and as for the rebinning, well, I don't think we had any specific issues with rebinning, but yes, of course, you have to do some rebinning to increase the signal to noise ratio.
All right, thank you. Perhaps we can take that offline. It sounds like an interesting discussion. Thank you so much. Can we have another round of applause?